Hey there, 10th graders, and welcome to today's explainer. So if you've been staring at chapter 12, surface areas and volumes, and feeling, well, just a little bit overwhelmed by that giant mountain of formulas, I want you to just take a deep breath. Seriously, we're going to throw out the memorization flashcards today. Instead, I'm going to give you what I like to call math X-ray vision. We're going to learn exactly how to look at complicated, real-world objects and mentally break them down into super simple pieces. By the end of this, you're going to be conquering these combination solids using pure logic, not just pure memory. Sound good? Let's get into it.
Okay, let's dive into this with a bit of a mystery. Imagine you're holding a solid wooden cone in one hand, right? And a solid wooden cylinder in the other. You do the math and calculate both of their total surface areas. But then you take some superglue, stick the flat base of that cone right onto the flat base of the cylinder, and press them together tight. Here's the million-dollar question. Is the total surface area of this brand new combined toy equal to the surface area of the cone plus the cylinder? Like, does it get bigger? Or does it actually get smaller? Keep that in the back of your mind because the answer to this is literally the secret key to this entire chapter.
So to really understand how shapes combine, we've got to activate that math X-ray vision I mentioned. Think about it. In our day-to-day lives, we rarely ever see perfectly mathematical standalone shapes, right? But you've definitely seen a medicine capsule, or maybe one of those massive oil trucks on the highway. At first glance, it looks like one big, complex shape. But look a little closer. It's actually just a basic cylinder right in the middle, capped with a hemisphere on the left and another hemisphere on the right. Spotting these basic, everyday building blocks? That's your absolute first clue in becoming a master shape detective.
Section 1, the missing surface mystery.
Now, what's really interesting about this is the trap a lot of people fall into. The single biggest mistake students make in Chapter 12 is assuming you can just add the total surface area of Shape 1 to the total surface area of Shape 2. But no way, that is absolutely wrong. Instead, the right way to think about this is entirely physical. The total surface area of a combined object is only the parts of the shape that your hands could actually touch if you are holding it right now.
Let's go right back to our superglue analogy for a second. When you take a hemisphere and a cone and you mash their flat, circular faces together to make a toy, what actually happens to those flat faces? Well, they're trapped inside the toy now. The glue is covering them up, and since they are totally hidden on the inside, they're no longer part of the surface. That specific surface area completely disappears from our calculation. Poof, gone.
Your textbook actually gives us a really beautiful official rule for this whole thing. It states, the total surface area of the new solid is the sum of the curved surface areas of each of the individual parts. Now, while that's perfectly true for shapes that are joined exactly edge to edge, I want you to remember our much simpler golden rule. Just calculate the area of the outer skin. It's that simple. If your hand can't feel it, your math shouldn't count it.
Section 2, becoming a shape detective.
Look, whenever we face a terrifyingly complex math problem, we absolutely do not panic. We just do what we always do, break it down into smaller, previously solved problems. And here is your foolproof 3-step detective method to do exactly that. Step 1, identify the individual base shapes. Step 2, find that hidden glued part. Like ask yourself what surface just got trapped inside. And step 3, add up only the visible, touchable areas. Honestly, if you follow this checklist, you literally cannot fail.
Section 3, solving the cube puzzle.
All right, let's put this into practice. Imagine this decorative wooden block is sitting right in front of you on your desk. I want you to visually paint this block in your mind. Imagine running your hands over the flat, smooth sides of the wooden cube at the bottom. But wait, as you reach the top, there's a smooth, round dome sticking out, a hemisphere. Let's say the cube has an edge of 5 centimeters and the hemisphere dome has a diameter of 4.2 centimeters. How on earth do we find the total surface area? Well, following our detective method, step 1 is just looking at the base shapes. Let's start with the cube. If this cube were completely alone, its total surface area is just 6 times the edge squared. Since the edge here is 5 centimeters, that's 6 times 5 times 5, which equals exactly 150 square centimeters. Boom. Easy, right? We've got our starting number. So the crucial point is right here in step 2. Is the whole top of that cube exposed? Nope. The hemisphere is sitting right on top of it. That means there's a hidden circle, the flat base of the hemisphere, trapped right between the dome and the cube. Because we can't touch that circle of wood, we absolutely must subtract it from our cube's total area. So we minus the area of a circle, which we all know is pi r squared. And now for step 3. We've subtracted the flat hidden circle, but we still have to add back the shiny, rounded dome on top.
the part our hands can actually feel. That dome is the curved surface area of the hemisphere. The formula for just the curved outer shell of a hemisphere is 2 pi r squared. So we're going to add that right into our equation. Just look at how beautifully our logical little story here matches up with the textbook's math formula. We didn't sit around memorizing this long string of algebra. We built it from scratch. The surface area of the block equals the total surface area of the cube minus the hidden base area of the hemisphere plus the curved surface area of the top hemisphere. You see? Algebra is really just a language describing the physical world we just built.
And when you actually plug the numbers in, 150 minus pi r squared plus 2 pi r squared, the math simplifies beautifully to just 150 plus pi r squared. Using our radius of 2.1 centimeters, that comes out to 150 plus 13.86, which means our final answer for the painted area of our decorative block is exactly 163.86 square centimeters. See that? You just successfully deconstructed and reconstructed a complex solid. Amazing.
Section 4, ready for exercise 12.1. And this brilliantly illustrates our main takeaways for today. Whether you're tackling example 1, 3, 4, or diving straight into exercise 12.1, the approach is exactly the same. First, deconstruct the real-world object into its basic spheres, cylinders, cones, or cubes. Next, hunt down those hidden glued surfaces and just kick them right out of your equation. And finally, sum up only the curved or flat areas that your hands could actually physically touch. So, you've totally mastered the outside skin of these objects. But before I let you go, I want you to think about what's happening on the inside. We know for sure that when we glue shapes together, that touching surface area completely disappears. But what if we hollowed out that combined shape and needed to fill it with water? Does the volume disappear too when shapes are glued together? Think on that for a bit, because that is exactly the mystery we're going to unravel in section 12.3 in our next explainer. Until then, keep that math X-ray vision turned on.
Hey everyone, welcome back. So today in this explainer, we're literally putting on our hard hats. We're going to think like master architects and figure out how to calculate the volume of complex, real-world 3D objects using simple, everyday shapes. If you've ever looked at a massive architectural structure or just a really tricky math problem and wondered where to even begin, you are entirely in the right place. We are going to build your conceptual mastery completely from the ground up.
All right, here's our blueprint for today. We're going to look at real-world math blocks, the absolute golden rule of volume, walk through example 7 with a solid toy, build some complex engineering models, tackle a really cool water displacement puzzle, and finally, build up our summary toolbox. Let's get right into it. Section 1. Real-world math blocks. Let's train our brains to see the math hiding right in plain sight. Imagine you're in the science lab, and you pick up a test tube. Now, if you suddenly needed to find exactly how much liquid it could hold, you're not going to find a magic test tube formula in your math book, right? But wait, look closely. You do know the formulas for a cylinder and a hemisphere. Just by visualizing an imaginary line right near the bottom, boom, you've turned an impossible shape into two incredibly simple ones. Or picture one of those massive trucks carrying water or oil down the highway. It looks totally intimidating, doesn't it? But this perfectly illustrates the exact same concept, just on a giant scale. If we visually take a saw and cut that tank right at the seams, we're left with one long cylinder in the middle and two hemispheres stuck perfectly to the ends, and you already know how to solve for those.
Moving on to Section 2, the golden rule of volume.
Okay, before we crunch any actual numbers today, we absolutely have to establish the most important rule for this entire chapter. There's a huge conceptual difference between surface area and volume. See, when you stick two solids together, some of their surface areas literally disappear where the objects touch. They hide. But volume? Volume never vanishes. Think of it like pouring a cup of water into a bowl of water. The total amount of water is simply the two amounts added together. It's that simple. The total volume of a combined solid is always just the sum of its parts.
All right, Section 3, Example 7, the solid toy. It's super easy to let complex word problems totally overwhelm you. But seriously, don't sweat it. Just follow this simple 3-step breakdown on our whiteboard to conquer literally any combined solid. Step 1. Identify your basic shapes. In this textbook example, we've got a hemisphere and a cone. Step 2. Pull out your trusted volume formulas for those specific shapes. And Step 3. Just add them together. So let's grab our known dimensions straight out of the textbook problem. We have a cone with a height of 2 centimeters.
It gives us a base diameter of 4 centimeters. But wait, you know the drill. We always want to convert that tricky diameter into our trusty, highly usable radius. So we just cut it in half to get 2 centimeters, and because they share the exact same base, our hemisphere also has a radius of 2 centimeters.
From there, thanks to our golden rule of volume, we just do the math for each individual piece. We use 2/3 pi r cubed for the hemisphere and 1/3 pi r squared h for the cone, and then we just add them perfectly together. See? It's just simple shapes stacked right on top of each other.
Let's step it up a notch with Section 4, Engineering Complex Models. Okay, we're going to act like real designers now with this awesome problem from Exercise 12.2. So, an engineering student named Rachel built a model out of a thin aluminum sheet. The problem tells us her model is shaped like a central cylinder with 2 cones attached to the ends. We know the total length is 12 centimeters, the overall diameter is 3 centimeters, and each cone is 2 centimeters tall. But here's the catch. To find the total volume, we first have to figure out the hidden height of that central cylinder.
And honestly, it's actually super easy to find that hidden dimension. By just visualizing the entire 12-centimeter model and subtracting those 2 2-centimeter cones off the ends, we easily discover that our central cylinder is exactly 8 centimeters tall. It's like a puzzle. See how pure logic totally solves the problem before the heavy math even begins?
Now, when you plug in your radius of 1.5 centimeters and all those different heights into the volume formulas and add them up, you are going to get a long, scary-looking string of fractions, pi symbols, and numbers. When you face a massive equation like this, absolutely do not panic. Take a breath and just solve it one simple block at a time. Calculate the cylinder volume, then calculate the cones, then just add them up. You've totally got this.
Next up, Section 5, the water displacement puzzle. Okay, let's tackle something a little bit trickier. We're going to combine everything we've learned about volume with the real-world physics of water displacement. The textbook throws us this mind-bending question. What happens when you drop 100 lead shots into an inverted cone that is completely full of water? It sounds like magic, but we're basically asked to find the exact volume of a single lead shot based entirely on the water that spills over the edge. It's pure, beautiful science and math coming together.
So let's visualize this setup. Imagine dropping those heavy little metal spheres into the full cone one by one. Sploosh! The water has absolutely nowhere to go but out, right? Basic physics tells us that the volume of the water that got pushed out and spilled onto the table, well, that has to be exactly equal to the total volume of those 100 spherical shots now sitting at the bottom of the cone.
The problem tells us that 1/4 of the water flows out. So by following 3 logical steps, we can turn a terrifying physics problem into basic arithmetic. First, calculate the total volume of the cone. Second, find 1/4 of that number. That's your spilled water, which is also the exact volume of the 100 spheres. So step 3, to find just one sphere, we simply divide that spilled water number by 100. By stepping back and visualizing it, basic multiplication and division absolutely saves the day.
Finally, Section 6, Summary, Building Your Toolbox. Let's take a look at what we've learned.
Let's review the incredible mathematical toolbox we've built today. Look at what you've achieved. According to the chapter summary, you are now fully equipped to deconstruct pretty much any combination of basic solids. Whether it's a simple toy, an oil tanker on the highway, or a complex aluminum engineering model, you have the skills to break it apart and calculate its exact properties.
And seriously, if you remember absolutely nothing else from this explainer, remember our golden rule. Volume never disappears. While surface areas might hide from you when shapes are glued together, volume always adds up perfectly.
It's like the saying goes, complex problems are just simple shapes stacked together. So the next time you look at a crazy architectural building or you open up a math exam to a seemingly impossible, intimidating question, what simple, basic shapes will you see hiding inside? You have the blueprint now. Go out there and start building.
So, do you know exactly where you're losing marks in Chapter 12? You know, I've spent years looking at thousands, literally thousands of SSLC math exam papers, holding that dreaded red pen. And let me tell you a little secret today. Securing a centum, getting that perfect 100 out of 100, it really isn't just about being a math genius. It's actually entirely about knowing the rubric. See, the examiners aren't out to trick you. They're looking for specific, highly predictable triggers to award you marks. And if you don't know what they're looking for, well, you're just leaving free marks on the table. Welcome to this explainer. Today, we're going to do something a bit different. I'm putting you right into the shoes of a veteran board evaluator. Our exact mission? dominating the Karnataka SSLC board exam, specifically targeting that highly competitive 81E math paper. We're going to rip apart Chapter 12, surface areas and volumes. But we're not relearning basic textbook definitions here. Oh no, we're looking exclusively at the official key answers, the evaluation schemes, and those high-yield exam patterns.
Okay, let's dive into this. Here's our game plan. First, we'll get inside the evaluator's mind. Then, we'll secure those one-mark formula directs, avoid the deadly TSA mark trap, crack combo volumes, steal the step marks, and finally, build your ultimate exam blueprint. All right, kicking things off with Part 1, inside the evaluator's mind and grading the rubric.
Here's the absolute biggest realization you need to have going into this exam. We don't grade genius, we grade the rubric. You see, SSLC evaluation is a strictly mechanical process. It's based entirely on an official key answer provided by the board. This means every single half mark is officially mapped out, way before we even see your paper. Honestly, this should instantly calm your exam anxiety. It means the whole system is completely predictable. You just got to know how to trigger those mapped out marks. Moving right along to Section 2, securing those one-mark formula directs, these are absolute examiner favorites. So the absolute easiest place to gather marks is the multiple choice section. Examiners love this. If you look at the recent SSLC board papers, you're going to routinely see direct formula questions, like the volume of a frustum of a cone, for instance. They absolutely love to test if you know it's 1/3 pi h times the sum of r1 squared, r2 squared, and r1 times r2. They'll also throw in the surface area of a sphere, 4 pi r squared, or the volume of a cone. These are literally guaranteed one-mark yields. Memorize them perfectly, because examiners rely on these to test your foundational recall before the real heavy lifting begins.
Now for Section 3, the TSA mark trap. This is exactly where top students end up losing marks.
Take a look at this classic exam question. It's a toy combining a cone mounted right on a hemisphere. Now picture yourself sitting in the exam hall. The clock is ticking down, and the question asks for the total surface area, or TSA, of this toy. How exactly do you calculate it?
Well, the ultimate student trap here is thinking that the total surface area of the combination equals the TSA of the cone plus the TSA of the hemisphere. Let me be clear, if you write this, you immediately lose marks. The evaluator way, the correct way, is to recognize that when solids are joined together, their internal faces vanish. You can't touch them anymore. So, the crucial point is that the total surface area of the toy is actually the curved surface area, the CSA of the cone, plus the CSA of the hemisphere. Please, whatever you do, do not add total surface areas together when shapes are combined.
All right, on to Section 4, cracking combo volumes and additive capacities. Now, while surface area loves to play tricks with hidden faces, volume is beautifully straightforward. Volume combinations simply represent the total space occupied by a solid. Unlike surface area, volume is strictly additive. If you've got a cone on top of a cylinder, you just add the two volume formulas together. Boom, done. And hey, here's a massive tip for your 2-mark or 3-mark written questions. If a problem says a cavity is hollowed out, like say a conical cavity drilled right out of a solid cylinder, you simply subtract the volume of the hollowed shape from the main shape. You add to build, and you subtract to hollow out. It really is that simple.
Let's hit Section 5, stealing the step marks. This is all about maximizing your partial credit.
Now, what's really interesting about this slide is that you're looking at the actual official 81E evaluator key answer. Notice those physical half marks written right next to the steps? If you need to find the volume of a combined shape, just writing the formula out in words, like volume of cylinder plus volume of hemisphere plus volume of cone, gets you a mark. Substituting the base formulas, that gets you another half mark. You're literally stealing partial credit before doing any of the heavy arithmetic. Even if your final calculation turns into a total mess because of exam pressure, you can still walk away with 80% of the marks for that question just by explicitly writing out these steps. And this brilliantly illustrates how we apply this exact strategy to a massive 5-mark question. Say you get a problem involving a cone and a hemisphere inside a water-filled cylinder. You might see this complex setup and totally panic. But wait, the official rubric awards half a mark just for finding the height using Pythagoras, half a mark for writing the volume of a cone formula, another half mark for substituting the values. You can lock in 2 or 3 marks immediately without even solving the final complex algebra. Seriously, never ever leave a question blank. Write down the given dimensions, write the relevant formulas. As an evaluator, I want to give you those half marks. Bringing it all together in Section 6, your exam blueprint and the evaluator's checklist.
Let's move forward and see how this builds your perfect answer. When I'm sitting there evaluating your paper, I have a mental checklist. Step 1, did the student write the given dimensions clearly? Step 2, did they explicitly write the combined formula in words and then the actual mathematical formula for the basic solids? Step 3, did they substitute the values correctly? And step 4, did they provide the final answer with the proper units? If you structure your answer exactly like this, you literally force me to give you the full 4 or 5 marks.
But be warned, there are common student mistakes that will instantly trigger my red pen, and I don't want you falling into these traps. First, forgetting to square the radius in the formula. You know, it happens all the time when you're under pressure. Second, exactly what we talked about earlier, adding total surface area instead of curved surface area for combined solids. Third, completely missing the final half mark because you wrote centimeters instead of centimeters squared for area or centimeters cubed for volume. And finally, panicking and leaving a blank. Remember, a blank page gets a 0. A page with a basic formula, that gets a half mark. So, I want you to walk into that exam hall with this high-yield memory mantra just playing on loop in your head. Say it with me. Secure the formula, secure the half mark, protect the units. First, write the formula down to prove you know the geometry. Second, substitute what you know to secure that sweet partial credit. And third, protect your hard work by triple-checking whether your final unit is squared for area or cubed for volume. All right, you now possess the evaluator's playbook. You know exactly what we're looking for, where those sneaky traps are hidden, and how to scientifically extract every single mark from the 81E math paper. So the only question left to ask yourself before you sit for that exam is this. Are you ready to stop losing silly marks and finally claim your centum? Because let me tell you, that 100 out of 100 is sitting right there, just waiting for you to take it. Best of luck and go dominate that exam.